prospective studies. If you wanted to learn more about these, you could do a search online, maybe go to Wikipedia. Some of these may not be easily identified from these names. I had to kind of guess their names. I got this from one website, and then I tried to kind of correlate it with something in Wikipedia. I wasn't completely successful. There's something called the British Doctors Cohort Study. Some doctors in Great Britain said they were going to track physicians over time. They sent out a questionnaire, I think it was probably 1951, and they asked various questions of the doctors, how old they were, what their health status was, whether or not they were overweight, underweight, where they lived, whether they smoked or not, and so forth and so on. As of 1951, there were suggestions that smoking was harmful to your health, but nothing definitive. Well, this was the first study that at least gave a lot of credence in a formal way to the fact that smoking has negative health consequences. Since that time, probably 10,000 studies have been done, and basically the same story. Smoking increases your risk of getting lung cancer, it increases your risk of cardiovascular diseases, increases your risk of a whole host of things, which your doctor will no doubt list in nauseating detail if you're still smoking. Alright, but anyway, they didn't really know, didn't have a clear idea whether or not smoking was the problem, because in Great Britain at the time they had a lot of air pollution in their cities, so the question was it the smoking was the cause, or was it maybe the air pollution in these cities? Well, they figured out at least the association was very strong between smoking and negative health consequences. Since that time, they've done just an extraordinary number of studies, some experiments, and now it's a done deal. I mean, everyone knows that smoking has negative health consequences. Something called the Framingham heart study, and this is actually still going on, not with the original participants, but with the third generation, and not the first generation they studied, but the second generation after this, they're now studying. This was the first study to clearly indicate there was a connection between high cholesterol and cardiovascular problems, and that there was a risk between hypertension, high blood pressure, and cardiovascular problems. It was not, I don't think it was clear before this time that these two things were connected. They used to think hypertension came with age and high cholesterol came with age, but that wasn't necessarily, if you will, the cause of cardiovascular problems. This study apparently said, the evidence was pretty strong. And again, they've done lots of studies since then, and so they tried both to control high cholesterol and hypertension. Now, the European Prospective Investigation into Cancer Nutrition, I think this took place in the 1990s, and basically the association there was a healthy intake of fruit and vegetables lowers the risk of various cancers. So that's been known, I think, for some time, and now the recommendations are stronger. So when you look at the recommended food groups, they always have veggies and fruits and so forth, and that's because there's not just this study, but many studies have shown basically the same thing. In 1976, they began an Earth's health study, and they were interested in what were the long-term consequences of the use of oral contraceptives, smoking, alcohol, and diet, and health outcomes. Okay? And I think this one is still going on as well. This was the doctor's cohort study ended in 2011, and the nurses study, at least from what I can tell, is still ongoing. They study these people, they track them, they publish papers in various journals, and a lot of our knowledge about what is associated we find evidence in these studies. Physicians' health study. This was, I think, done in the United States, probably in the 1980s. And what they found was that a low dosage aspirin regimen, there's a low dosage you get in your grocery store, reduces the risk of a first heart attack for those who have increased risk for that. So most males, by the time they get to my age, they're saying stop eating, do nothing but exercise, and take a low dosage aspirin. All right, and I think most men are probably on that regimen. There was a study that came out not too long ago that said, wait. There are some risks. Often there are risks associated with this. In the case of aspirin, you can have acid reflux disease from it. So you have to be, any information you hear, you need to check with your doctor because there are always sorts of caveats and qualifications and so forth and so on. But all of a sudden, probably by the end of the 1980s, doctors are starting to tell older males you need to take a little aspirin every day. Again, some people probably don't want to do that because the reduction in risk in heart attack may, for some individuals, be raised for the risk of acid reflux maybe goes up, and you have to kind of balance those things. For example, males who have a history of heart attacks in their families probably want to do something like this, but males that don't, maybe not. Again, it's the doctor that decides this, but this is a study that kind of led to that. The Women's Health Initiative, and I think this was done in the United States. And one of the things they did, and I don't know all the things they tracked, but hormone replacement therapy increases the risk of a heart attack. So it used to be during the, I think it was, it would have been during the 80s, what they did is they had women on, when they went into menopause, they had them in hormone replacement therapy. Now they're much more careful about who gets on that, because they know there are certain risks associated with that. Again, keep in mind, as your doctor is supposed to know about this. I'm just trying to point out some of the prospective studies and some of the things that came about as a result of that. There's another one, and this was, let me see if I can identify that one. I know it's here. And let's see here. This is some data that was collected by a colonel in Afghanistan, Colonel Michael Wirtz. And basically what he did is for all 500 Americans who were wounded in maybe the battalion or the army, whatever the unit or organization he was associated with, he tracked everything about those soldiers, how they were injured, what sort of medical treatment they got, whether or not there was a dog or a bomb-sniffing dog in the unit that he was a part of. All that information was recorded, and then as a consequence of that, they can look at the long-term health outcomes from that. Who benefited from what types of treatment on the battlefield, what types of treatment at field hospitals, and then maybe what sorts of treatment after that once they came back to the United States. And I guess he did this on his own. Of course, doctors know about this stuff, and things like this will be extremely useful, not only to soldiers but also to civilians. They'll probably fold some of these ideas into the care of civilians. And sometimes it's just the collecting of data, the very careful collection of data that helps us understand what takes place, not only in the medical field but in other areas as well. All right, so that's prospective studies. And now what we want to do is we want to learn one of the important things in life, and that's how to gamble. All right. So what we're going to do is we're going to look at three, I don't know if we'll get to all three, but we'll get to at least two types of random phenomenon. One is coin tossing, one is rolling dice, and the other one is picking cards. And sometimes what we do is we repeat that. So for example, on a coin, we can flip it not just once, we can flip it multiple times. All right, and rolling a die, we can roll a die multiple times. Now picking cards is kind of interesting, especially if we do it more than once. So I take a well-shuffled deck, we always assume the deck is well-shuffled, and I pull a card out. It makes a difference if I select a second card by what I do next. If I pull out a card and note what it is, if I don't put it back in, versus I put it back in and reshuffle, actually our probabilities change. For example, suppose I have a deck of cards, and I pull out an ace of, say, ace of diamonds, and I don't put it back in. What's the chance I would pull out an ace of diamonds again? 0. If I put it back in and reshuffle it, it's not likely I'll get the ace of diamonds, but it's possible. That's an example of whether you have sampling with replacement or sampling without. In a deck of cards, that's important. In a deck of 1,000,000 cards, basically it's not. Okay, in other words, there might be a slight difference in mathematics, but not very important. Okay. Let's take a look at some of these ideas in more concrete fashion. Let's take and talk about flipping a coin. Well, all right, now what we do here is we're going to look at very simple experiments or random phenomenon, and then we'll make them more complex. So the first experiment or phenomenon we'll look at is tossing a coin. This is an example of known unknowns. What we call the sample space is a description of everything that we can observe. We can either have a head or a tail. Now in mathematics, we invent notation as a way of kind of making our ideas more concrete and then also not being overwhelmed, if you will, by all the writing. So this is what we do. We use the letter S to represent the sample space. I'm going to put down an equality sign. I'm going to put up what we call a curly bracket. You can find those on your keyboard. I'm going to put down the capital letter H and the capital letter T. And I'm going to put down another, what we call a closing curly bracket. Now this symbol H is an abbreviation for head. The symbol T is an abbreviation for tail. On the left-hand side, I have the letter S, which is an abbreviation, basically a sample space. And then I have the equality symbol. If you've had some set theory before, that's where this equality comes from. These two brackets are a way of just delimiting or indicating the beginning and the ending of my description. And in this case, I'm saying symbolically, I have a sample space with two possible outcomes, something at H and something at tail. And I just associate the head with flipping a coin and seeing a head on the top. And T is associated with flipping a coin and seeing a tail on the top. All right, now let's look at a slightly more complicated experiment. And that is rolling a die. Now, I've shown you different types of dies, but let's focus on what we sometimes refer to as a fair six-sided die. So rolling a fair 6-sided die. Now what we could do is the sample space, we could draw it graphically. I could have one dot on the top, or I think they're called pips, or I could have 2, or maybe 3, and then I could have up to 6. But I don't want to write the symbols down here. So what we do is we associate with each of these outcomes, if you will, just the numbers 1 through 6. And I'll write something like the following. Operator? Oops, thank you. Uh-oh, a loaded die. Actually, there are such things. That's why I say a fair die. Whoops. You can actually buy dice that are not fair. And basically what's happened is they've taken one of these faces and they put a heavy weight on one side. So what happens is when you roll it, that side has a higher propensity of landing down. If you buy them online, they're called magician's dice. If you play with them, that's called illegal. All right. So I don't know what the rules are in Oregon and in Nevada. They're probably a lot stricter because they want, they don't mind policing you and taking your money in the casino, but they want to do it fairly, right, with fair dice. All right, so these are 2 examples of random phenomenon. Now what I'm going to do here is the following, is I'm going to introduce the notion of probability. And I'll write it down in full or in written form, and then we'll abbreviate it. So the probability of a head is a number, in particular 1/2, but we want to avoid writing this all down, so we will abbreviate that by this symbol right here. P stands for probability, H stands for a head. The probability of a tail is also 1/2, and we would write that as probability of T, or in that fashion. Why 1/2? Well, there are a couple ways of thinking about this. One way is as follows. If I flip a coin repeatedly, about half the times I should get heads, and about half the time I should get tails. That hopefully seems plausible. Okay? Another way of thinking about that is in advance of flipping a coin, I don't know what I'm going to get, so whatever number I associated with those 2 outcomes ought to be the same. Well, what we can do here is we basically, probabilities are always numbers between 0 and 1. There can never be a probability greater than 1, and there can never be a probability less than 0. Now, probabilities can be expressed as fractions, or as decimals, or as percentages. Percentages have to be between 0 and 100%. Okay, now let's talk about probability in this case over here. What's the probability of getting a 1? 1 out of 6. That's also the probability of getting a 2. Probability of getting a 3. And so forth on up to the probability of getting a 6. All right. Now, we're going to play a game, and the game is based on rolling a die. And what I'm going to do is we're going to have three players. Three players in a game where a die is rolled once. So one player is going to win if either a 1 or a 2 is observed on the top face. So it would be first player. Second player is going to win if there's a 3 or 4 on the top face. And the third player, first, second, third, will win if there's a 5 or a 6. Okay, now, what is the probability that the first player wins? 1/3. Yeah. So this is how we would rank that. First of all, rather than writing all this down, usually what we do is we use capital letters to represent these descriptions. These are actually what we call events. So these are events. And I'll symbolize this with A, this with B, and this with C. The probability of A, we can think of, well, there are 2 outcomes out of a total of 6, or 1/3, that the first player will win. The probability that the second player wins is symbolized by that. That's also 2 out of 6, and that's 1/3. And the probability of C is 2 out of 6, and that's 1/3. All right, now, if you have such a game, all right, and maybe what happens is you become part of the game and you do this game repeatedly, and everyone has to put in, say, a quarter to play the game, and the person who wins gets the quarter. So that he gets his own quarter, or she gets his own quarter back, and then the quarters from the 2 other players. Now, in this case, basically it's anyone's guess who will be in the lead at the end. There's no reason to prefer that the first player, second, or third is going to be the winner in the long term. Okay, now, suppose, on the other hand, we have another game. So I have, in this case, 2 players. And we'll designate, let's use different letters here. Let's see, how about D will consist of 1, 2, 3, and 4. And then E will consist of outcomes of 5 and 6. And so that there's fairness in this, I will be the player who wins. And the second player is the sucker. Okay? Why is the second player a sucker? Well, I mean, the probability of a D is 4 out of 6, and that's 2/3. And the probability of E, all right, is equal to 2/6, or 1/3. Now, the only reason that this is appropriate is if we pay the same amount to play this game. If both of us put in a quarter, In the long term, I win. All right? Which reminds me of the story. Remember, old age and treachery will outdo youth and enthusiasm and dead and not. All right. So in this case, I think everyone sees I'm more likely to win than this person here. Now, what we could do is we could actually adjust the payments. And let's see, I guess if I put in, let's see, 3 halves, let's see, for every coin this person, I put in 1.5 coins. That's going to work out. No, for every, if I put in, say, 3 quarters and this, 2 quarters, and this person puts in 1 quarter, in the long run it will even out. Even though I will win more often, I'll win back my 2 quarters plus another quarter of this person, but this person every now and then will get my 2 quarters plus his own or her own quarter, all right? So if we adjust the betting, in fact, we can turn this into what we call a fair game. The significance here, though, is to use the notion of event. The event D consists of the outcomes 1, 2, 3, and 4. The event E, all right, consists of the outcomes 5 and 6.
These are not mutually exclusive.
Well, okay. These 2 events are mutually exclusive. The word mutually exclusive means nothing in common. Now, this would be a funny game if D consisted of 1 through 4, and this consisted of 4 through 6, because in that case, well, if a 4 occurs, who wins? Maybe we could call that a draw or something like that. But for purposes of analysis here, this is all the further I want to go for the moment. We'll talk about all these things as we go forward. All right, now let's take a look at again in this example here. We're rolling a fair 6-sided die, and the sample space is described in this fashion. And what I've done over here is I've cooked up a game where I've invented some terms. These are what we call events. The probability of all these events are the same. Here's a new game. The probability of the 2 events are different. And basically,
the probability of the games are different here. Is that you roll 1 dice?
well, in this case, the change is here I have 3 players,
Yeah.
and they all have equal number of outcomes in their events by which they win. Now over here, what I've done is I've divided the outcomes into 2 parts. More outcomes are associated with my winning than outcomes of the sucker's position.
Is it outcome who's winning?
Now in general, this is what we would do. Let A, actually let's use a new symbol, H, no, not H. I'll go A. Let A represent an event from a sample space S. What do I mean by that? The sample space is, if you've had some set theory, that's called the universal set. It's, if you will, the collection of outcomes about which we're talking about. There isn't, I mean, there's nothing else in the universe. when we roll a six-sided die, except the outcome 1 through 6. So that's the universe. The event A, all right, would be some portion of those outcomes. This is what we do. Assuming I have a simple case like this, n at A is the number of outcomes in A, n at S is equal to the number of outcomes in the sample space, and the probability of A is in fact the number in A divided by the number in S. That's basically what I've been doing all along here. Now be advised that this would break down if I don't have a fair die. In fact, you can get some of these magician's dice are so strong that when you roll them, you can almost be certain of what you're getting on top if you're careful. So that doesn't, you know, what that does is it changes all these probabilities. It changes the story completely. When I talk about a fair die, I'm talking about something like this, where I toss it up. I don't know what's going to come up. A 5. I have no idea, once I let go of it, what to predict it's going to be. It's going to be 1 through 6. If this were weighted on one side, I would probably generally want to bet on the opposite side. That would be more likely outcome. Okay? So in this assignment of probabilities, we are assuming that each one of these outcomes, so to speak, is equally likely. Now, as we get into more complicated situations, we'll have to adjust these roles. Let's go back to again this example here where I have some a die, I'm rolling it once, and I have 6 possible outcomes. Let's identify M as being the event consisting of 2, 4, and 6. Now, one thing here in this case, the probability of M would be equal to 3 out of 6 or 1/2. Now, there's a symbol, well, let's call the complement of M, which is symbolized in a couple ways. Let me put down the various ways. This author, I think, does the following. He puts a C in the upper right-hand corner. Some authors will do the following. They'll put a tilde in front of M, and some authors will put a bar above M. I think this is the notation that the author uses. Now, the probability of M is 1/2. What's the probability of the complement of M? Oops. Well, first of all, what do we mean by that? That's good. Well, a complement of M, again, typically represented by this or that. This is the author's notation, as I recall. It would be everything in the sample space which is not found in M. So this would be 1, 3, and 5. What is the probability of the complement? It's also 3 out of 6, or 1/2. Now there are some, a couple things to be said here. Instead of tossing a coin, where I have heads associated with a head, and that's probability is 1/2, and tail is probability 1/2. Instead, I could roll a die. And I could associate with M, say, heads. What's the probability of an M? It's 1/2. It's the same as the probability of a head. Okay, and then the complement of M just also has the same probability. Create a new event. Let's call it event T. And we'll make that, say, 1 and 6. The smallest value and the largest. What's the complement of T? It's everything in my sample space that is not part of T. So this would be 2, 3, 4, and 5. All right. Now, what's the probability of T? Well, it'd be 2, 6, or 1/3. What's the probability of the complement of T? 4, 6, or 2/3. Notice the probability of an event plus the probability of the complement of an event must be 1. That's a rule that always holds in probability. I'm going to be listing rules next week. I want to make sure I cover as many ideas here. Let's be a little more sophisticated. Now we're going to roll an 8-sided die. And again, I'm going to assume it's a fair 8-sided die. And for 8-sided dice, usually the faces are labeled 1 through 8. All right, now suppose I invent an event called A, which is a power. Now let's say a prime number. Sometimes I can give a verbal description of an event, and I'm going to tell you what this event is. A prime number is a whole number or a natural number that can be divided only by itself and by 1. But in addition, it has to be bigger than 1. So let me write down if you will, what outcomes fit this description. First of all, 1 is not prime because primes have to be bigger than 1. That's just in the definition itself. What about 2? 2 is prime because it's divisible by itself, it's divisible by 1, and no other, what we call natural number, will divide it. So 2 is a part of the prime numbers here. What about 3? 3 is prime as well. 3 is divisible only by 3 and by 1. How about 4? 4, no, it's not because it's divisible by 4, by 1, and by 2. What about 5? 5 is prime as well. 6? No. 7? Yep. Okay. And 8 is not. 8 is divisible by 8, 1, 2, and 4. All right. What's the probability of A? 4 out of 8, or 1/2. What's the complement of A? Well, it's everything in here, but not down here. So that's going to be a 1, a 4, a 6, and an 8. Let me just check my notes here so that. All right, things get more interesting if we do something repeatedly. Let's consider tossing a coin 3 times. Now, in each toss, I'll have an outcome where on the top it will be a head or a tail. So, tossing a coin 3 times. Now, the sample space can be written the following way. If I toss a coin 3 times, every time or every trial, the top could be a head. So that's one possibility. I could have 2 heads followed by a tail. I could have a head, a tail, and a head. Or I could have a tail, head, and a head. We've got more possibilities. The first outcome here, the top is all the same. They're all heads. This, and that, one of the 3 is a tail. Now what I can do is I can have tail, tail, head, tail, head, tail, head, tail, tail, and finally I can have all tails. How many outcomes are there in S? There's 8. Now it turns out that in many cases, when we do something repeatedly, it's helpful to use what we call a tree diagram. And I'm going to sketch a tree diagram here. Right? If I've got 9 things up there, I'm going to have a lot of explaining to do. Do I have 9 things up there?
No, I'm asking.
Well, okay, which one did I miss?
I don't know which one I just counted because the usual should be 3.
It should be 2 to the 3rd power, which is 8. Yeah. That's why I know there are 8. All right, now, what we do sometimes is to kind of understand these better, we draw a tree diagram, and we think of starting at this point. This is called a node. And the first time I toss the coin, I could get a head or a tail. Now, the second time I toss it, suppose I had a head the first time, I can get a head and a tail, all right? And over here, if the first time I toss it, I have a tail, I can have the same outcomes as the second toss. So these are called nodes. First node is I flip a coin, I get either a head or a tail. Then depending on what I've had before, if I've had a head first, I flip it again, I get a head or a tail. And we just repeat that, same basic pattern, all across the tree. This is not the most interesting of trees. We'll find others that are more. All right, now, it is also the case, what we can do here is the following. The probability of getting a head here is 1/2. So I'm going to put that in parentheses. And the probability of getting a tail is 1/2 as well. Now, once I've tossed the coin once and I have a head, the probabilities of a head and a tail, again, are the same, they're 1/2. And the same thing is true on the third toss, if you will. If I had a head, then I can either have a head or a tail. And the probability, once I get to this point, once I've tossed a coin twice and observed 2 heads, the probability of a head is 1/2, and the probability of a tail is 1/2. Now, if I think of starting here and going to here, going to here, and here, then what I've had is a head, head, and head. The probability of a head is, in fact, in this case, because of independence, is simply 1/2 times 1/2 times 1/2, which is 1/8. And if I do the computations all the way down, on the right-hand side, well, in graph theory, we call these leaves. This is not graph theory. We don't want to confuse it with stem plots. No. The far right-hand side, how's that? All right, now, I have 8 outcomes, and actually each one of these are equally likely. There's no reason to suppose or believe in advance that anyone would be more favored than the other. So actually, they're all going to have a probability of 1/8. All right, now, in games of like this, we can do this analysis. This isn't so valuable in the case of tossing coins. It is in drawing cards when you don't put cards back into the deck. Let's see how that holds. Suppose I'm going to draw 2 cards from a deck of cards, and I'm going to do it without replacement. So, 2 cards are drawn from a deck without replacement. And I'm going to break this, shall we say, I'm going to create 2 situations. I either get a diamond or I get something else. So, and what I'm going to do is I'm going to put a tilde in front of the diamond to indicate something other than a diamond. So it would be a club, heart, or a spade. Now, for those of you who have lived a sheltered life, or actually a card deck in my overhead, we'll get to that in a moment. Maybe not today. In a deck of cards, there are 52 cards. The 52 cards are broken into 4 suits. The suits are diamonds, hearts, clubs, and spades. They have those symbols on it. And the cards are labeled 2 through 10. Jack, Queen, King, and Ace. So there are a total of 13 cards in every suit. So if I have a well-shuffled deck, there are 13 diamonds out of 52. So what is the probability of getting a diamond the first time I draw a card? It would be 13 out of 52. The remaining cards, which would be 39 out of 52, that's the probability of getting something other than a diamond. Now, this is where things get interesting. Suppose I have drawn a card out and it's a diamond. How likely is it that I'm going to get another diamond out? Well, now what I have is I only have 12 diamonds out of 51 cards. So the probability here would be 12 out of 51. The probability of getting something other than a diamond would be, I guess that's going to be what? 39 out of 51. Now, let's do it again. Suppose, here I'm only saying describe. Suppose I stretch the game and I say, let's do it a third time. Suppose I get a diamond followed by another diamond. What's the likelihood of getting another diamond? Well, there are only going to be 11 diamonds left out of 50. And not a diamond, there will be, again, 39 out of 50. All right, so moving from left to right, again, this is a tree, these are nodes. In going from here to here, we think of drawing a card from our deck and getting a diamond. First time around, the probability of a diamond is 13 out of 52. However, if I don't put the card back in, then I only have 12 out of 51 which are diamonds, 39 out of 51 which are not diamonds, so my probabilities have changed. Now, if I draw out 2 diamonds, I'm at this situation. Again, I can potentially draw another diamond, but there are only 11 left out of 50. And here, there's still 39 out of 50 of the non-diamonds. Now, Ben Affleck, thank you, Ben, recently got in the news. And he was playing blackjack, supposedly, and the casino that he was gambling at, he was playing blackjack, and he got kicked out. And why did he get kicked out? Well, he was counting cards. Basically, counting cards is a more complicated situation than what I have here. In this case, if I know I have 2 diamonds out, I know my probability of getting a diamond for the next draw is 1 down, and the probability I could get something else is 1 up. When you count cards, what you're doing is you're looking at what has been played, what information is public, and then adjusting probabilities on that basis. Now, there's probably more to the story about Ben Affleck and this casino, because they said, oh, he can play any game he wants, he just can't play 21, or blackjack. I don't know if he was counting cards. Usually casinos have so many decks of cards now, it's pretty hard to count cards. He might have been trying, he might have been successful, I don't know. If he's successful at doing this, he must have pretty good memory and pretty good computational skills. If nothing else, remember, in gambling, all publicity is good. For both the casino and probably for Ben Affleck. Ben Affleck will get his lawyers, they'll sit down with the lawyers with the casinos, they'll work out a deal. The casino will say, we're sorry, Ben, you can come back, you can play. But anyway, I mean, the reason casinos like this publicity is because they attract more customers. Okay?
How they know he's counting cards? Is it
Well,
always
they don't.
Yeah.
If they don't, in a casino, basically you are there with the casino's permission. If they suspect you of counting cards in Nevada, they will ask you to leave. I don't know whether Ben was counting cards or not. Yeah, the thing is, what it does is it alters the likelihood that the house is going to win. Blackjack is the only game where you can adjust your strategy and improve your odds of winning from the house. All the other games you play there, the house wins on average. They don't build these nice buildings with all this fancy stuff to give you money. I know that's going to break your heart. That's the way, it's the golden rule. He or she who has the gold makes the rules. Casinos are not in the business of giving out money. They're in the business of having a net income. That's where their profit comes from. They want the games to be interesting, exciting. They want people to come there and have fun. But mostly they want them to come and leave at least some of their cash behind. It couldn't be any other way. Well, I've gone over my limits. I'm out of time. They're kind of pulling me off stage. So I'll see you next week. We won't have a quiz because I like to do my quiz on second quiz on probability.